Hi, I'm Daniel Chan from UNSW Sydney. This is Extension 3 Mathematics for Talented High School Students. In this video, I want to look at the following question, which is to express a function f of x of a real variable as a power series. So in other words, in the form of this infinite sum from n equals 0 up to infinity of a n x to the n. So you want f of x to equal this power series at least for all values of x which are sufficiently small for which this power series converges nicely. And what do we mean by for all x sufficiently small? So usually we describe it in the following way. We want to look at all the values of x which satisfy a condition like this. They're all the x between, say, minus r up to r, where r is just some positive real number that depends on the question or the function that you're looking at. Okay, so the set of all these x's, of course, will include 0 because we're going to assume r is some positive real, but it will include some more values of real numbers as well, those whose absolute value is strictly less than r. The set of all these x's is usually denoted like this. It's got a round bracket minus r comma r and then a closing round bracket. And this is an example of something called an open interval because it doesn't contain the endpoints. So it doesn't include x equals minus r or x equals r. Okay. So what we want to do is basically we want to find this power series such that we can also find this positive real number r such that this power series will converge for all these values of x, and the value it converges to is this f of x. And the question is, how do you find this power series? Okay, and also, well, does it really exist? And so the answer here is very nicely given by Taylor's theorem. There are several versions of it, and I'll present one of them here. And it's a little bit complicated, but before launching into it, I want to motivate it with the following thought experiment. Okay, so the following heuristic argument, which actually tells us the only possible answer to this question. In other words, it's going to tell us what this sequence of coefficients has to be, okay, but it won't tell you whether you actually get equality in that case. So how does that work? Okay, so let's go bit by bit. So the first thing you want to do is basically this question is asking you to solve for the coefficients of this power series. So how do you do that? Okay, so let's start with the first one, which is a0, the constant term or the coefficient of x to the 0. Well, the easiest way to have a look at that is, well, let's just look at f of 0. F of 0 is equal to, well, all the terms which have higher powers of x, x to the 1, x squared, x cubed, they'll go to 0, so that just gives you a0. So that tells you what the first coefficient is, which is very nice. But how do you get the next coefficient? So the way you do that is the following. We're going to differentiate this f prime of x. And remember, if you have a situation where you have this radius of convergence, so the ratios of these ANs heads towards some real number, okay, positive real number, then you'll have absolute convergence, and you can also differentiate term by term. So we'll differentiate this term by term to get the following. So you have the sum from n greater than or equal to 1 up to infinity of, you'll have an here, but you'll also have n times x to the n minus 1. And what does this imply? Okay. Well, again, we can apply the same trick as we did in the first case here. If we substitute in x equals 0, then most of the terms will vanish. Only when you have x to the 0, which occurs when n equals 1, do you get a term that's left over. So when you look at that term, that will tell you that f prime of 0 is equal to, you'll have n equals 1 is the only term you'll pick up here, so you have 1 times a1. That's just a1. Okay, so let's keep going. This is looking good. We've solved for 2 of the terms. Of course, we need to get infinitely many of them. So let's differentiate again. And now you have the following. You differentiate this again, so not only will you have the n, but you'll have an n minus 1 out the front. And then you have this power series. Okay, and what does that tell you? Okay, so we're going to do the same trick. We'll substitute when x equals 0. So what does this imply? So this implies that f double prime of 0 equals, in this case, you look at n equals 2, that's the term that gives you the constant term in this power series. So you have 2 times 1, okay, so that's 2a2. And that allows you to solve for a2. a2 is half of the second derivative of f at 0. And then of course you can keep going, and I hope you can see the pattern here, and you can look at the kth derivative of x. And here the pattern is, now you look at n greater than or equal to k, and now you keep bringing down this superscript here, this index. So you go n minus 1, and you'll have k of them. So you go to n minus k plus 1, a n x to the n minus k. Okay, so that's the value that you have. And then you can also look for the case where x equals 0. So what does this tell you about a k in this case? So when you put x equals 0, you look at the term where n equals k. So when n equals k, what do you have here? N equals k, so you have k times k minus 1 all the way down to n minus k here gives you 1. So that's k factorial times ak. So that means what you want to do is you want to have a look at the kth derivative of f at 0 and divide this by k factorial. And so that gives you the kth term. Okay, so it's quite a nice argument, and it tells you what the only possible power series that you can use to express this function. And of course, to do this, you have to assume that you have a function f which is infinitely differentiable at 0, and it gives you the coefficients in terms of the derivatives of f at 0. So the kth coefficient, ak, is just the kth derivative of f at 0 divided by k factorial. Okay, so that motivates Taylor's theorem, which is the following. Okay, it's going to express this function f as something that's a bit similar to this, okay, which will allow us to actually show when you do have equality. So suppose now f has continuous k plus first derivatives on some open interval from minus r up to r. Okay, so we're going to suppose that there's some positive real number r, and on this interval here, so for all x between minus r and r, okay, f has is a function defined on this, and it has all these derivatives. Okay, then what we're going to do is we're going to write f of x as equal to all the terms that you see here going up to x to the k. So this should be a k here. Let me rewrite that. So x to the k here. And so what's that? So you have f of 0, that's my a0 term. Then your a1x term here should be f prime of 0. So this one here, f prime of 0 times x. And what's your x squared term here? The x squared term here, remember, is your has coefficient a2, and that's given by this here. Okay, so that's going to be the second derivative of f at 0 divided by 2. And then you go all the way up to this kth one here, which would be the kth derivative of f at 0 divided by k factorial. Okay, so you subtract off the first k terms that you would expect from here, from f of x, and then you'll have some remainder term. I'll just call this rk of x. Okay, so certainly you can define rk of x to be the difference of this f of x with this thing, which is the first k terms that you would expect of this power series expressing f of x. Okay, or rather the first k plus 1 terms that you have here, so the terms going up to x to the k. And the question that you want to answer is, well, what can you say about this remainder term? You want it to be such that when k goes towards infinity, okay, so you get more and more of these terms in here, this goes to 0. So we need some control over the remainder, and in particular we want to somehow control how big it is. We want to make it go to 0 as k goes off to infinity. So Taylor's theorem gives us some expression for this remainder term that allows us to control it, okay? The remainder term, it's a little bit tricky how it works, but this is all it is, okay? It's equal to 1 on k factorial, the integral of the following function, and it's the integral from 0 to x, because this is something that is a function of x, and the integrand here is the k plus first derivative of f times x minus t to the k dt, okay? So here we fix the x, so this is for x, you have this is true, and then you're integrating this over t here. And that gives you Taylor's theorem, which tells you the remainder term when you try to express this f of x as the first k plus 1 terms of what you expect to be the power series for f of x, okay, plus a remainder term. Before proving Taylor's theorem, let's have a look at this theorem in action with the following function. Here I want to take f of x is equal to the exponential function e to the x. So what does Taylor's theorem tell you? Okay, so let's rewrite this formula out. So we have e to the x here, and then what we do is we look at the f is the exponential function. We look at all the derivatives of this exponential function up to the kth derivative. So here that's just the exponential function itself, and we evaluate them at 0, okay? So we're evaluating e to the x at 0, that gives us 1. So all these derivatives of f at 0, they're all equal to 1. And so that gives us this polynomial here in x, okay? And the coefficients of that polynomial are just given by replacing all these derivatives of f by 1. So you just get on the denominator these factorials. So here you'll get the first one, you'll just get is 1. So this here you'll get as a coefficient of 1 for x, and then you'll get x squared on 2, which you can also write as x 2 factorial, plus all the way up to 1 on k factorial, x to the k. And then you have this remainder term, k of x. And what we want to show is that this actually, when you take k going off to infinity, will give us the power series representation for e to the x. In other words, you will get a convergent, in fact an absolutely convergent power series such that what value does it converge to? It will converge to e of x. And the way we'll show that is by showing this rk of x will go towards 0 by showing that it is bounded by something that goes towards 0. Okay, so let's see, as k goes to infinity, let's see what happens to the this rk of x. Okay, so what is this equal to? So we just use the formula here, and you just write this out. So firstly, you'll have 1 on k factorial. Let's take the absolute value now. So we'll take the absolute value of this integral from 0 to x. The derivative here, we're looking at the exponential function, so all the derivatives are just e to the x, so here it's e to the t. And then you'll have here x minus t to the k dt. And we want to look at the absolute value of that. Okay, and we want to basically find a bound on that is still sufficiently small that it goes towards 0 as k goes to infinity. That's what we want to do. So let's just bound that. So how are we going to do that? So we're going to do it in the following way. Okay, so firstly is that what is a bound on this integral? Well, if you, it's like a sum. When you sum the absolute values of numbers, okay, that gives you an upper bound on the original sum. And here, if you instead integrate the absolute value of the integrand, that will give you an upper bound on the absolute value of this integrand here. So that's what we're going to do. We're going to look at the absolute value of this integrand. Okay, so we'll have a 1 on k factorial here, and then we'll also have here the absolute value of e to the t. Now, what's the what can you say about that? Well, this will vary over this interval from 0 to x. And what's the biggest value it can have? Well, remember the exponential function is increasing, so it looks like it's e to the x. But if it's x is negative, then I guess the biggest value is e to the 0, which is 1. So here, the biggest value that this e to the t can take is either e to the 0, which is 1, or e to the x. And then now we can bound the rest of it. So we pulled out the biggest value that this can have. We're going to replace this positive value e to the t with the biggest value it can have, which is either 1 or e to the x, if x is positive. And then we look at the absolute value of the rest. So we have here integral from 0 to x of x minus t to the k dt. Okay, so what's that equal to? I guess here we should use the absolute value. And then what happens? So now we want to look at what this is. So we're going to bound this as well. So this is less than or equal to. And it's quite easy to do a change of variable and just integrate this. And what you'll get, of course, is just x to the k plus 1 divided by k plus 1. So when you integrate that, you'll have here, you can do a change of variables if you like, or just integrate it using the standard tricks in calculus, and you'll get for this integral just x to the k plus 1 divided by k plus 1. So the k plus 1 factor, I'll stick on this factorial, and then you'll have this max term here, and then you'll have here x to the k plus 1. And then what we want to do is show that as k goes to infinity, this goes towards 0, in which case the remainder term has to go towards 0 as well. And that will show you that if we continue this off for k equals infinity, then this power series will converge, and will also converge to e of x. But how do we do that? How do we know that this is going to go towards 0? So the way I'm going to write this out is as follows, okay? So I'm going to write this out as the max I'll pull out first. And then here, note this is a product of k plus 1 terms. That's going to be in the numerator. And this is also a product of k plus 1 terms. And the k plus 1 terms is in the denominator. So I'm going to take one of these absolute values of x, and I'm going to put it onto the first, the smallest factor here, that's 1. And then I'm going to pick the next absolute value of x and multiply it by the 2 here. And then I'm just going to keep going until I get the last one. Okay, so that's what we have here. And what do we know? So the key thing to realize here is that we're going to look at this for each and every value of x. And what I want to say is that for each and every value of x, this is going to go towards 0. So why is that? Well, once you fix this absolute value of x, there will be a time when this denominator here, these denominators keep getting bigger and bigger, but the numerators here stay fixed. So after a while, this new denominator will exceed the value of this numerator, and in fact it will keep going higher and higher, and as a result, what you're multiplying with will be numbers smaller than 1, and those numbers actually will go towards 0. So that means that it doesn't matter how big this value was here and how big these initial values are, when you keep multiplying these smaller and smaller positive fractions, this will go towards 0. And so that means that that implies that e to the x is equal to, well, we can have a look at this entire power series here, which is given by 1 on k factorial x to the k, as k goes from 0 to infinity. And this is for all x. And that's how you use Taylor's theorem. And what we've shown in this example here is that the exponential function for x, it can be expressed as a convergent power series, and it's this convergent power series here. It's a sum from k equals 0 to infinity of x to the k on k factorial. Let's now go ahead and prove Taylor's theorem. Okay, so what we'll do is that we'll look at this remainder term here, and we're going to prove that this formula here by integration by parts. So the first thing is we need to make some observations about the derivatives of this remainder term rk. So let's look firstly at the derivatives, which are the earlier ones, which have I is less than or equal to k. So that's the first k derivatives, and let's see what the derivatives of this remainder term are. And to do that, it's quite simple, because remember, when we wrote this f of x, when we motivated this expression for f of x as, well, eventually it was going to be a power series. We wanted to solve for all these an's, but for the moment here we just have the first few terms up to the x to the k term, the first k plus 1 terms, and then we have this remainder. When we worked out the coefficients of this polynomial part here, how did we do it? We did it so that basically the first k derivatives of this polynomial part at 0, those derivatives at 0 match the derivatives of f at 0 as well. Okay, so let's just check. Okay, so for example, let's forget this remainder term. You just look at this polynomial part. Okay, so the 0th derivative, what do you get there? The 0th derivative is just the first term, so you get f of 0 both sides. If you look at the first derivative, of course, you'll differentiate this, the constant term drops, and when you evaluate 0, you just pick up this f prime of 0. So this polynomial has the same first derivative at 0 as f, and similarly all the way down to the kth derivative here at 0. Okay, so the kth derivative of this polynomial at 0 is also f to the k 0. Okay, so that means that, well, if you subtract from both sides, what can you say about the remainder term? The remainder term, if you look at the derivatives from I equals 0 up to k, those ith derivatives at 0, that's just equal to 0. But if you differentiate more than k times, so if I is greater than k, what happens? When I is greater than k, of course, this polynomial part will disappear. Okay, so that means that when you differentiate more than k times, the derivative of f is the same as the derivative of rk. So here the ith derivative rk is the same as the ith derivative of I. So they're facts that we're going to need to look at. So what we'll do is we'll look at this expression, this integral expression for the remainder term, and analyze it a little bit more. Okay, so let's look at that. So what I shall do is I shall put the k factorial inside here. So we have here integral from 0 up to x of f to the k plus 1 t on x minus t to the k on k factorial, and that's dt. And the key point here is that since we're looking at the k plus first derivative here, so that's bigger than the k, that's beyond the kth derivative, I can replace this f here with the remainder term. So let's just do that. So that's the derivative from 0 to x of rk to the k plus 1 t x minus t to the k on k factorial dt. So it looks still pretty messy here. So how are we going to integrate this part? So the key to this is we're going to use integration by parts. Okay, so what we'll do is when we use integration by parts, there's a term like this, okay, which is, so to speak, a definite integral. We fix the x here, so this is for each and every x. We have this is true. The x's being in this open interval here. So we'll have a definite integral part. So what we're going to do is we're going to integrate this term. Okay, so the integral of this we can pick to be the kth derivative instead of rk. And then we have this term here, which is x minus t to the k on k factorial. And we'll look at the values from x to 0. And then we have to subtract. What we'll do is we'll have this term here. So this is from 0 to x, r, k, k, t. But we have to differentiate this term. When we differentiate this term, what happens here? So firstly, this power goes down by 1. The k comes downstairs, so it cancels with the biggest factor here to give you only k minus 1 factorial. There's also a derivative of the x minus t term, so that's a negative, so this is actually a plus, and this is dt. Okay, so what's happened here, just to analyze the integrals, what integral have you swapped it with? So this integral here is a little bit nicer. It looks a lot like this, except for this remainder term here, instead of looking at the k plus first derivative, you look at the kth derivative. That's the change in this factor here. What about here? Here you've got a similar factor, okay? But instead of looking at the kth power of x minus t, you look at the k minus first power, and instead of having k factorial on bottom, you look at k minus 1 factorial on bottom. So basically, to go from here to here, you've just reduced from k to k minus 1. Okay, so that's rather nice that you've simplified things like that. What about this definite integral part here? What's happening here? Okay, so let's see what happens. So the easiest part to analyze is when t equals x. When t equals x, you get x minus x, so this is going to be 0 here. What about when t equals 0? When t equals 0, you've got a derivative of r at 0. And remember from here what we saw, if we look at derivatives at 0 of r, okay, and that derivative is an ith derivative where I is between 0 and k, then you're going to get 0. So this term is also 0. So that means that we can forget about this term. And then once we forget about this term, we can look at this and say, well, let's apply integration by parts again. And we'll do something similar. We'll integrate this term and differentiate this term. And what that will do is we'll reduce the k's and k minus 1 here to, instead of the kth derivative, the k minus first derivative, and in here, instead of the k minus first power, the k minus second power, and you'll have a k minus 2 factorial instead of a k minus 1 factorial. Okay, you'll also have a term like this, but the same reasoning, because you're looking at derivatives, in this case now the k minus first derivative of rk at 0, that will still be 0, and this other term will also get you a 0 too when t equals x. So that means that you can keep going down, but you can't go down forever, so where do you stop? So you stop at the following place. You can keep going down until, I guess, k equals 1. When k equals 1, then you have to stop, okay? You can't keep going. So there, let's have a look at k equals 1. So you have rk prime of t. K equals 1 means that this is something to the 0, so that's just a 1, and then you'll have 0 factorial, which is just 1. So you just have the integral from 0 to x of the derivative of rk to t. And of course, that equals rk of x. So we've shown that this integral expression here is indeed equal to this remainder term, where the remainder term is just defined to be f of x minus, well, we looked at what should be the expression for the power series for f, okay, and we took the terms up to x to the k, the first k plus 1 term, so to speak, okay, and basically this remainder term is just f minus this k plus 1 terms here, and that proves Taylor's theorem. And just to sum up what we've done here, and what's the most important thing about Taylor's theorem is, so firstly, it's not true that for any function f can you express it as a convergent power series. Okay, so that's the first point. But when you can, usually Taylor's theorem is going to tell you how to do that. Okay, so you have to do some work, as we saw in the previous example. So what you do is you look at this remainder term here. Okay, and then it's a little bit complicated, and there are other versions of Taylor's theorem as well, but this one's nice and easy to prove, and it's useful enough to use quite often. If you can show that as k goes off to infinity, this goes towards 0, then that means that when you look at the corresponding power series, okay, where the nth term is going to be given by an x to the n, where this coefficient an is the nth derivative of f at 0 divided by n factorial. Okay, suppose you have that. In that case, f of x is equal to that. For what values? For all values of x which is on this open interval where we said f has continuous k plus first derivatives. Or actually, I guess, not k plus first derivatives, but all derivatives. Okay, then you have this equality for those values of x. And in that case, we call this series, which converges to this f of x on that open interval, the Maclaurin series, or the Taylor series for f at 0. So I hope now you can also use Taylor's theorem to express functions as power series.